Let's start with our first example of a newer protocol, Multipath TCP. So what is the motivation for this? Well, for example, we have a device like a mobile phone, and your mobile phone typically has an antenna for the cellular system, so that's LTE, 5G, but also has an antenna for your wireless LAN, Wi-Fi. Different wireless systems, and both systems can be used to connect to, let's say, the internet. Goes different paths, different routers, so in the end, you connect to the internet. And in the internet, you might have a server. So if traffic flows from and to a server, you can take two paths, one across the cellular and one over the wireless LAN system. So depending where you have connectivity, maybe higher data rate, maybe lower cost, etc. So why not having a connection across two paths, which doesn't work with the classical TCP. And also I will come back to pooling resources. That's also a requirement in the context of content delivery networks. I will come back in the last chapter. So the idea is, well, multiple paths. Especially if you have different paths to choose from, maybe you want to move traffic away from congested to failed links. So for example, if you have no more wireless LAN connectivity, then you want to cut this connection and all the traffic flows across the cellular network. So that would be a nice idea. But for the application running here, nothing changes. It's still a single service access point. So this increases reliability, flexibility, efficiency. So that's the idea. So why not looking at many different resources as if they were a single one? So you have a choice, let's say, of different networks, different paths with different properties. But from the application point of view, this is basically like one pooled resource. So that's the basic idea. So if you have sources, different destinations, could be on a single machine, for example, then why not looking at this combination of all these resources as a single pooled one? And the question is, on which layer should we implement the resource pooling, bring this all together? Link layer is difficult because there are different links. Network layer, no, because different paths. Application layer, then we have to change the application. So the choice is the transport layer. On a transport layer, you can do this pooling. So that's one of the ideas of this multipath TCP, resource pooling, but everything is based on TCP principles. And we need some additional logical connections. Based on TCP principles, this reminds you, well, there was a problem, ossification, I will come back to this. And also maybe fairness and all these things. So why doing so? Well, TCP is well known. It's the transport protocol of the internet. So, you know, the web, the classical web and email and peer-to-peer and everything runs using TCP. And TCP already includes reliability, includes congestion control, and we want to be able for an incremental deployment. Remember, you cannot simply change everything and now you use something completely new everywhere. No, incremental deployment. There are different RFCs for this, but how does it work? So multipath TCP. Now let's start with a very naive approach. A naive approach would be, hey, I've got two different paths, a blue one and a yellow one. So, okay, for load balancing reasons or for whatever, I can start sending my SYN, SYN-ACK, and ACK. This sets up the connection, okay, across the blue path. There might be many routers in it. Now think of maybe this is the cellular path and that's the Wi-Fi path or whatever. And then I can send my first data. Perfect. And the naive solution would be, oh, cool. Now the other side knows that we have a connection because I started with my three-way handshake. Okay, perfect. And now I can send data. Perfect, because the receiver knows port address that it comes from me. So that's the naive solution. It would work. Why not? Because IP transports also this new data packet. Why not? From a source to a destination. And only here in the destination I decide, now this packet goes this way, this packet goes that way, but we stay within a single TCP connection. Perfect. Works. Nope. Doesn't work. Why? Not in today's internet. Because we have the middle boxes. What happens if you approach, just a simple example, approach your net box with just a data packet without setting up a connection before? The box would say, where does this packet belong to? I mean, I have to translate addresses, whatever. No, never seen a connection setup. So even a simple net box has never seen a connection setup. Then there are many more complex middle boxes. They've never seen a setup following the rules of TCP, and thus they would simply discard the packet. So this doesn't work because of the middle boxes. In a pure, let's say, academic network, it would work, sure. I mean, IP would simply forward then the packets across different paths and everything is fine. Not in today's internet. So, what do? We cannot invent something completely different. We have to solve the issue with the middle boxes. So the idea is that a multipath TCP connection, if you have a multipath TCP, you set up a connection, but this connection consists of many subflows. And all the subflows are regular TCP flows. And the idea is that the hosts on both sides, they glue together all the subflows to create then the multipath TCP connection. And all the subflows, they appear like a regular TCP connection along the path. So for all the middle boxes in between, this looks like a regular TCP connection. The middle boxes are not aware of the fact that this TCP connection is part of a larger multipath flow. I will show you this in some more detail. So the idea is that we still have the application. Application is not aware of anything. The application uses the normal socket interface. The application should be aware of this normal socket interface. So you pump your data via a socket, and now we squeeze in the multipath TCP layer. And this layer now manages the different subflows that come from different regular TCP connections. And for the TCP connections, we use the TCP the operating system has anyway. So IP is normal and all the TCPs are normal. So we set up several TCP connections called subflows. But they look like regular TCP connections. And this means, oh, well, we don't have a problem with this ossification because we use regular TCP connections. From the viewpoint of the network, many TCP connections, that's it. So what again was this regular TCP connection? Well, we have the three-way handshake, and we are allowed in the TCP standard to send special options in the SYN segments. Okay, so that's one of the ideas, as we will see. And then we send all the segments in sequence. There's no gap, and this is the normal TCP connection, and we terminate it by FIN typically. So how does it look like? Well, now again, our setting with the blue path and the yellow path, for example, cellular and Wi-Fi. So we start initiating the connection, a SYN request, and now we set a certain option in this first packet, which is possible following the standard, but it could be the case that already here a middle box says, no, I don't know this option, I kick out the packet. So this might be the case. Then in real implementations, we fall back to a regular TCP connection, and that's it, and we cannot use multipath TCP. But if this option goes through, because the middle boxes don't look at it or don't react, whatever, we set up a normal TCP connection, SYN, SYNAC, ACK. The only thing is that we transfer certain tokens, token X and token Y. Why do we need them? Because after setting up this connection, we can start using the blue one. Maybe we want to start a new subflow. Suddenly, we have a Wi-Fi connectivity. Hey, cool. Then we start a new subflow, but this subflow now looks for all the middle boxes like a regular TCP connection. SYN, SYNAC, ACK. And now we can use also the yellow one. But both end systems have to be able to bring the data together to fuse it again, and this is why we use the tokens. So our server here gave us a token, and that's exactly the token we use here. And then the server knows, oh, well, the yellow one, indeed, this belongs to the blue one. Answers with our token, and this means, okay, perfect. We set up a yellow flow and a blue flow, and they both belong to the same multipath flow. That's the idea. But all those subflows, so the yellow subflow and the blue subflow, they look like a regular TCP connection for all the middle boxes. With the only problem, maybe they don't like these options. Okay, so the subflows, well, you have to be able to differentiate them. So two different subflows, they have to be different, at least either in the ports, local, remote, or the IP addresses. And that's the case. Just in a simple example, typically in your mobile phone, you get a cellular IP address, and over your Wi-Fi system, you get a Wi-Fi IP address. So you have different IP addresses for the connections, local IP addresses. And what's also quite good, the number of the subflows, that may change during the lifetime of multipath TCP connections. So maybe you have a long-term connection to a server, and maybe there's a Wi-Fi coming up, the Wi-Fi goes, and that's the next one coming up and going, and you have all the time the same additional connectivity with the help of the cellular network. So cellular acts as a fallback. If everything fails, then you fall back to the cellular. If both subflows break down, you have a problem. But as long as you have one subflow, well, you have no problem and can continue with the multipath TCP connection. So now, how do you transfer data? Okay, let's start with the naive approach first. Well, okay, now we have established our two connections. That's fine. Regular TCP connections. Now let's send sequence number, a letter A. We get the acknowledgement, as we know. So we acknowledge this is the next byte we expect. Fine. Now we think, okay, cool. This is what the server expects. Now let's send the next byte across the yellow path. This is fine because we have a connection set up and the server will answer and says, okay, 125 is the next one. And then the idea could be, why not doing this kind of, let's say, 50-50 load balancing, send the 126 over the blue one and the 127 then over the yellow one. Yes, looks nice, but although we have established the subflows, this doesn't work. This simply doesn't work. Why? Again, we have the middle boxes. Although we have the subflows, what happens? Now, again, we send this, our sequence number A, we get the acknowledgement, and now we send the B there and we get the acknowledgement back. And now let's assume we only have such a middle box on the blue path, and the next was this 125. There are middle boxes. They check for the sequence numbers and they see, wait, there's something missing. There are middle boxes that perform the acknowledgement on behalf of the systems behind the middle boxes. And they will see, uh-oh, something is missing here. They do not know anything about the transport that went across the yellow path. So this will fail. So although both are valid TCP connections, blue and yellow, if we have certain types of middle boxes here on the blue path, this middle box will detect, oh, there's a gap in between. Well, yes, I know, this should be the job of the end system. But, as I told you, the middle boxes may interfere for many purposes. So, okay, doesn't work. So what is the solution here? The solution is Multipath TCP introduces 2 levels of sequence numbers. There's one type of sequence number. That's the number of the bytes in the overall byte stream. So you get from across the socket, you get your byte stream. This is where you have your byte stream from the application. And the application is not aware of these different paths. And this is where we virtually exchange our data sequence numbers. So that's the byte stream. And then we have our subflows. And the subflows should behave like real valid TCP connections. And TCP connections, you remember, well, they try to fill the gaps and all these things. And this is why we have regular TCP sequence number for each subflow. And they have nothing in common because these are independent subflows. So each subflow does the regular TCP job for sequence numbers, acknowledgement, retransmission. And then we have these overall byte stream sequence numbers, the data sequence numbers, that take care of, well, overall, if something went wrong, if something is missing, if a whole flow breaks down. Could be the case you lose your Wi-Fi connection and then suddenly this connection is gone. And this has to be healed with the help of the data sequence numbers because the other TCP flows know nothing about this. So now, how does it work in today's internet? And we have these middle boxes somewhere in between. So we send our data in a flow with a TCP, regular TCP sequence number. So that's what we know from our TCP. And additionally, our data sequence number. Telling now, let's assume this is our very first byte. This is why we have the sequence number here set as 0. We get acknowledgement back, and this is our regular TCP acknowledgement. So tell me, okay, 124 is the next I expect. Plus, I get back an acknowledgement for the overall data stream. I expect the next one to be 1. This is a pure multipath TCP end-to-end issue. Then I use the other path for sending the next byte. A complete different sequence number. This sequence number 456 has nothing to do with the 123. And I will get back an answer. And you see here sequence number and acknowledgement. This is regular TCP stuff. But now, this sequence number and the acknowledgement, this is exactly the sequence number that is the next one, the expected one for this acknowledgement. Now for the middle boxes, this looks like a regular transmission. Now we can transmit our C, the next byte, as you can see. And the next byte now has the correct sequence number from a TCP's point of view. You see, that's the correct one. And no middle box will complain. And you will get back an answer. So this is the solution. So you have 2 sequence numbers. One for the subflow, following the regular TCP rules, and one for the overall multipath byte stream. What happens in a case of a loss of data? It might be the case. I mean, regular paths, you lose something. So, for example, we lose the A here. Okay, lost. And we send the B over the yellow path. What will the server return for the successful transmission of the B? it will tell us everything is fine on this subflow, but I acknowledge 0. Yes, thanks for sending the B, but I'm still missing the very first byte with the sequence number 0. So if this subflow, now assuming the subflow is completely lost, we lost the connectivity, so this path doesn't exist anymore, we have to recover from this lost byte in this case using the yellow path. So what do? We now, and that's the interesting part, retransmit the A over the yellow path, but as you see, we use the correct sequence number that follows this one. You see, oops. So from the sequence number point of view in the subflow, now this is the reversed order, but we know the original order by using the correct overall sequence number of 0. And then we get the acknowledgement for this. Again, on the subflow, from TCP's perspective, everything is fine, 458. And from the overall perspective, now we get the 2 as the next expected byte. So here you see this interplay between these different subflow sequence numbers and the overall sequence number. And this is how Multipath TCP works. The history, quite interesting. So 2008, it started, working group 9, first RFC, first implementations came out, and we had a lot of commercial support here. You see in Android support and iOS and so on, so different implementations. And there's a quite nice video showing this, how it works. And this really shows, okay, research can advance the internet, although we have these problems with the middleboxes, etc., etc. Okay, there are some larger use cases, for example, in Korea to offer high data rates to mobile phone users. That was one of the first usage scenarios. You see, okay, transmit across over Wi-Fi and 4G LTE network at the same time for high data rates. And quite famous, Siri on Apple phone uses multipath. So this is also, if available, then you go across the Wi-Fi. If not, then you can fall back to 3G at that time, or LTE or 5G networks now. So this is since more than 10 years. So quite successful, and this is used and supported by all the operating systems. So summary. So why was it successful? Well, one part is it operates like TCP. If we have TCP endpoints, everything is fine. So incremental deployment is possible. There's always a fallback to pure TCP. And for the network, it behaves like TCP, many TCP connections. So there's some signaling involved. And yes, there are some possibilities that also the application layer may control a bit more if you want to use multipath or not. But you can also use it without and let then the layer decide what's going on. Interesting, it uses TCP mechanisms. Think of the ossification. Yeah, we have to stay with TCP, but we have multiple paths, have typically different IP addresses, and create subflows. But the subflows themselves, they are TCP connections. And they're all mapped then to a single multipath TCP connection. This is why we have the 2 different sequence number spaces for the overall multipath connection and for the individual subflows. So the transmitted data, all the subflows, they have their own sequence number. Yeah, well known from this is TCP, and the connection itself has a 64-bit sequence number. So that's the idea. And this multipath layer in between then does the mapping, and has to do the reassembly and also the retransmission. And we have then these 2 layers also for the acknowledgements. We have the regular TCP acknowledgements. This is regular TCP stuff. And then we have on the higher layer, this multipath layer, also acknowledgement for the data sequence, the byte stream here. So that's the idea. And also there's some fairness involved, etc., like for TCP. So some questions about it. So going back, what was the main motivation? Why using Multipath TCP? What was the basic idea? And why can't we simply send the different data packets via different paths? I mean, we have a normal network, we have IP, and IP forwards everything. That's fine. Why shouldn't this simply work? And we have also seen how does this Multipath TCP then circumvent the ossification, and this is the main reason for why this could be successful, why we can use Multipath TCP, because there are also some other protocols that were not successful because they violated something. And here Multipath TCP did it in a more clever way.